Yeah, so thank you all for being to this last session and the marathon of talks this afternoon. But I'm really excited to share with you all this new graph visualization project we've been working on at Georgia Tech. So likely many people know that there's many types of data and natural phenomenon that can be represented as network graphs. So these are things like biological networks, social networks, and like the power grids. But visualizing these graphs becomes really hard, especially when they get really big, because oftentimes they turn into these giant hairballs, like people like to call them, like this thing behind me. And in fact, this graph behind me, in keeping with the IUI theme, is actually related to machine learning a little bit. So every node in this graph is a word from Wikipedia, and we connect two words if the distance between these two words in some learned word embedding, like glove, for example, is really small. So this is actually a graph generated from a word embedding. And there's a lot of graphs that exist like this in nature and just in many other domains. And a big problem of understanding what's inside of these graphs is this topic called graph sensemaking. So when it comes to graph sensemaking, there's two sort of views that people generally look at. One is this global view, where you're looking at sort of the overall structure of this entire graph. And another one is the local view, where you're maybe looking at just one node or one edge. And two modes of exploration that go hand in hand here is this notion of free exploration, where you're just sort of browsing this big graph, or targeted exploration when you're looking at one specific node or one edge, like I mentioned earlier. So what do we mean by structure and nodes here? By structure, we mean things like quasi-cliques or cliques. These are a set of nodes where they share connections between every other member in that set. Or maybe your problem is really focused on doing triangle counting. So you're looking for how many triangles exist in your graph. And by important nodes, we mean nodes that have many, many connections. So they have a high degree. Or maybe you're looking for nodes that are connecting two different communities, like this one in the bottom right, where you have some node that's bridging two distinct little quasi-cliques there as well. So there's been two major approaches that have gone about tackling graph sensemaking, the first one being data mining. So this is really concerning some automatic methods to do summarization or clustering on big graphs that are dealing with millions or billions of entities. And then human-computer interaction, which is, like you all know, is a little bit more iterative, human-focused, and concerns itself more with the interactive visualization side. But in this paper from VLDB in 2017, what the authors did was survey a bunch of graph analysts, I think on the order of hundreds, to find out the state of the field, to see what are the biggest problems that are going on right now. And two big problems, by far, that are affecting most graph analysts are scalability and visualization. So as graphs become bigger, analysts want to scale their algorithms, and they also want to not lose this notion of visualization to understand what's going on in the graph. So that's the exact two problems we set to solve in this work that I'm going to show today. And so the example I want to give is like, what if we were able to take some big hairball graph and we were actually able to split it apart and divide it into a bunch of nice little components where each component has a couple of interesting properties that you can then further explore, such as this example in 3D behind me. And this is exactly what we did with this paper. So this is Atlas. This is an interactive graph exploration system that wields a scalable edge decomposition algorithm. And we're going to go into what that means in a little bit here. What Atlas does is it separates large graphs into what we're calling graph layers. And each layer is revealing some peculiar subgraph structure. And another benefit of Atlas as well is that you're able to visualize this local structure with the context of your entire graph. There's also a bit.ly link up here that'll link you to all the code. Everything here is open source. I'll also put that link at the very end of the talk too, so if you don't get a chance to write it down right now. So how do we actually go about splitting graphs into all these different layers? I just want to run you through a quick little algorithm example so you get a feel of how this algorithm actually works, because we're going to be leveraging it here in the future. So to start, we have one pre-computation step where we just compute the degree of the graph. So this is just counting the number of edges that are going into each node. And there's this one parameter we have to keep track of called the peel. And what we want to do at each iteration of this algorithm is ask, are there any nodes in the graph that have a degree less than or equal to the peel? So if our peel is 1, we want to find any nodes here that have a degree less than or equal to 1. And you see it's those 3 there on the far right side. And when we find those nodes, we actually remove them from the graph, and then we update the corresponding degree. So that new node in the middle that had a degree of 5 now is a degree of 2. When there are no such nodes with a degree less than or equal to 1, we then iterate the peel value. So we'll make peel go from 1 to 2. We'll ask the same question, are there any nodes that have degree less than or equal to 2 in this remaining graph? We see there's a few here, so we'll remove them, increase our peel one more time to 3, And now you see that the remaining part of the graph, we sort of peeled away all these small, less degree vertices, and we found the most dense region in the middle. And when we've done that, we actually take the edges between those nodes, and we label them with the peel value that we've computed. So each edge has one unique value that corresponds to the highest peel value that we found. So then the last step we do is we take these edges, we remove them from the original graph, and we do everything again. So you see this is actually a deterministic algorithm, and it has no hyperparameters. So we'll just continue on with this process. We reset our peel to 1. You see all these nodes over here with degree 1, we'll remove those. That last one that gets shrunk down, we'll remove it as well. We'll then increase our peel to 2. And then we'll found this little triangle here in the bottom left, so we'll label its edges as having peel 2. Remove those edges, and you likely see what the last step's going to be. We now are left with this sparse little star that we'll just label its edges as having peel 1. So we've now had a unique assignment of numbers, these peel values, to every edge in our graph. And if I color this a little bit more suggestively, you'll be able to see what we're calling graph layers in that initial 3D visualization we had earlier. So graph layer 3 was that original dense layer that we found at the very beginning. And as you see, as you sort of go down the number of graph layers, you get to more sparse, typically more sparse structures. There's a number of really interesting mathematical properties about these graph layers as well, but for the sake of the talk, we'll omit those. They're in the paper. But there's actually 3 nodes that I accidentally just spoiled my little joke here, but there's 3 special nodes that are actually in between multiple graph layers. So these are nodes that share edges that exist between 2 different graph layers, so they don't exist within one single one. So these are what we're calling vertex clones, and these nodes are potentially really useful to be picking out in a graph, because what we have here are nodes that are playing multiple roles inside of a graph, so they're part of multiple communities at once. So we want to leverage this component as well. So that's just a quick little demo of how the algorithm works, just to get a feel of it. So we were able to implement this on a multi-threaded CPU implementation. And here's just a few results from the graphs that we decomposed. There's a lot more in the paper, but the punchline is this thing is very fast and very scalable. So given a graph like this Amazon one with 1 million edges, we can decompose that into 6 layers in about 1/10 of a second. And given the graph here at the bottom that has over 117 million edges, we can decompose that into 91 different layers in only about 1.5 minutes. And what's really nice here is that the time complexity of this algorithm is just dependent on the number of edges in your graph and the number of layers that it produces. But in practice, as you can see, the number of layers is often much, much smaller than the number of edges. So this runs in about linear time. And if you're really interested on just the algorithm side, myself and some other high-performance computing co-authors wrote this paper that was at IEEE Big Data just a couple of months ago, where we just looked at that one component of peeling away nodes to get to the dense region. And the punchline is, if you use a GPU, you move these computations to a graphics processing unit, and you use a dynamic graph data structure, you're actually able to get 4 to 8 times speed up over just those results I showed on the previous slide. Okay, so that's enough for the algorithm part here. Hopefully I've convinced you that this thing is quite scalable and is giving some nice results. So what I want to do is actually just walk through a demo of how our tool actually leverages this algorithm. So what we're going to do is look at that word embedding graph from the previous slide at the very beginning. And just to remind you, each word or each node is a word from Wikipedia. There's about 66,000 here. And then each edge connects 2 words if the distance between them in the word embedding space is really small. So let's get started here. Our tool Atlas has 3 main views. So on the left, we have this decomposition view. In the middle, we have this summarization called the graph ribbon of the entire decomposition. And on the right, we have the layers view. So let's go into each one of these a little bit more in depth. In the middle is a summarization of all the different graph layers that our algorithm has found. And we give a little glyph to each layer that has a couple of metrics we'll explain. But a user is able to come in here and selectively visualize which layers they want to see. So if we just select a bunch of these, we'll show them on the left-hand side. Users can zoom and pan in this whole view. But what we want to do is actually leverage the layer number as a z-coordinate to adjust the height. So we're actually able to make this 3D representation of the entire graph decomposition. And there's a number of interactions we provide too. So users can scale, zoom, and morph this graph in order to explore it a little bit better. So then if we now look at the graph ribbon, this part in the middle of the UI, It summarizes each layer, like I mentioned. So up here, we can show a quick screenshot of what each of these glyphs represents. So we have the layer number. We also encode the number of edges and nodes that exist in that layer. And then we color the bar according to how dense that layer is as well. So are there a lot of edges compared to the number of nodes, or is it a rather sparse layer? So for the example we can look at, we can actually load one layer in the left and in the right-hand side. So we can look at layer 8 here, which if you can see is a really dark layer. So this gives us some hint that there could be some really tight clusters. And indeed, we see that there are a bunch of small little components. But on the right-hand side, we can actually redraw this layer independent of the rest of the graph. So then we can reveal that there's actually a bunch of small quasi-cliques going on in this layer that the algorithms found. And then what we can do on the right-hand side is actually filter out those cliques by the size of them, so we can get rid of some of the smaller ones. And then as you hover over any one of these nodes, we also highlight their one-hop nearest neighbor, so you can quickly get a sense of what these nodes are connected to. So it looks like this quasi-clique is a number of Asian cities that this word embedding is found. And this one down here looks like a bunch of familial relationships. So these are words that the embedding has pulled out. So this is a nice little debugging technique to make sure that your embedding has learned the proper things. So then I also want to remind you that we have this notion of vertex clones. So these are knowns that exist in multiple layers at once. So we can actually toggle the clones toggle here, and we'll color nodes and scale them by how many clones they have in this entire graph. So what you can see here is that the bigger nodes show that they have multiple roles and existences in the whole graph, and the smaller ones may only have a few. So this word right here, dismayed, looks like we found this component, dismayed, horrified, annoyed, puzzled, some negative, surprising type words. But dismayed has a couple of other clones. So if we bring up another layer that it exists in, namely layer 5, you see that dismayed actually exists in 2 layers. And to emphasize that, if you drag any node that has a clone in another layer, we'll actually sync those positions across layers. So that blue dot that was dragging right there. So we can now go into this new layer we've navigated to. We can do some other layout techniques like laying out the graph layer independent in the browser using force-directed layouts. We can once again filter out some of the smaller components and then zoom in on the component that we were led to from the word dismayed. So another interesting thing that we can do in Atlas is click a few nodes and then click the path button, which will draw a shortest path between any 2 nodes you select. And then as you select more nodes, you can actually compute a shortest path from this new node to the already existing shortest path. So what this does is give you a way to build up a shortest path net of your entire component. So you're able to find the quickest ways that information can flow from within a component. And what we see here is that in the middle of this component that we're looking at, there's words like surprised and surprising that are these sort of neutral-like words, but then as we build up this shortest path, we actually see that there's positive surprise words, this little click that's attached on, like words like unbelievable and surprisingly, and a negative click like what we led to with dismayed and bemused and things like that. There's also this contour map toggle that you can toggle on. So if you don't want to look at all the nodes and edges and want a bit more of an abstract view, we support that as well. So we just compute contour maps around every single component in that layer. So that's just a quick demo. There's actually a number of different interactions that we support in Atlas that I didn't have time to show today. But just as a quick summary, we go over this little component that we found in the paper as well. But the general flow is that we have this big 3D decomposition overview. We're able to summarize, we're able to summarize the entire decomposition in the middle with the graph ribbon. And then you're able to find different components and cliques that may share some semantic relationships within this word embedding graph. Okay, so now at the very end here, I just want to go over a quick user study that we ran with Atlas. So we invited 3 graph analysts who, in their daily work, are often given large sets of graph data where they have no idea what's going on inside of it. 2 of the participants recorded this happens daily, and 1 other one weekly. So the goal here was to give them our tool Atlas that will run the decomposition on a number of different graphs. And their goal was to mimic what they do in their own practice, which is just to spot any interesting patterns or nodes that they might come across. So some just quick findings that we can highlight is that the 3D view was really used as an overview of their entire graph. When they didn't know what's inside of it, they found it was really helpful just to get a feel for the entire graph where they're not looking at one specific entity or one specific value, but they're just trying to see how this entire graph was broken apart and how it behaves. In the graph ribbon, the summarization in the middle, and the layers view were used a bit more precisely and analytically. By far the most frequently used interaction was the show nearest neighbor function. So when you hover over a node just to see the one-hop neighbors, that was used time and time again throughout the study. Another finding we had is linking all these graph substructures together. So what we initially thought was that users were just going to go to the graph ribbon and then click some layers, look at them, delete them, click some new layers. But what we found is that Vertex Clones actually provided a really nice traversal mechanism to explore between different layers. So users would often find some interesting layer they'd want to look at initially and then sort of jump off to other layers using clones and using nodes that already exist. And then lastly, one of our participants said there was an interesting connection to cybersecurity, particularly in the case of anomaly detection. So when you can find one clone that maybe has, or one node that has 20 clones, it could be some suspicious machine or computer that is firing a bunch of connections to some other computer network, and that could be worth investigating. Or for example, there could be one node that only has one clone and is playing a very singular role in your graph, and that could also be worth exploring. So just to wrap up some future work here, there could be some potential future directions to automatically suggest interesting layers as opposed to just a visual encoding. There could be some algorithmic way to suggest which layer to start with. We haven't, all the graphs we looked at were also static, so just at one time point, but it could be worth looking at decomposing graphs that vary over time. And then also some visual scalability techniques just to help with those hairball messes as well. So these are things like supernoding, edge bundling, and then some better motif algorithm computation to find out what sort of layers or what sort of components could be within a layer. And with that, I'm all done. So I just want to emphasize that both the visualization and the algorithm are open sourced, all on GitHub. You can use it on your own graph data today. We have a README of how to load in your own graph, like a CSV or an edgeless file, decompose it, and then load it in the tool itself. And I just want to thank my co-authors as well. And if we have time, which I think we do, happy to take any questions. Thank you.
We have time for about 1 or 2 quick questions.
Went a little bit long there. Sorry about that.
Right. Well, I can start off. So 3D and graphs, these two things don't, in general in Viz, we generally question about the usability of that. And one of your results are actually that people found that good for an overview. What do you think, or what do you observe it was about the 3D representation that they felt was good?
Right. Yeah. So one interesting thing about this graph decomposition is that the topmost layer is typically the most dense layer. So what actually happens is as you walk down the layers, you find the most dense things, and then you sort of graduate into this sparse and tree and star-like structure. So when you use a 3D view, you're actually able to split this whole graph, and you see that the dense things are rising to the top, and all this sort of sparse, sort of tangly mess sort of sinks to the bottom. So it's a lot easier when you're just rotating this thing by yourself to see which of these layers are actually this really tight click, and maybe that's some component that you're really looking for.
It's almost like a filtering mechanism by...
Exactly,
okay.
right.
Yeah, there's one question.
Hi, great presentation.
Thank you.
I didn't understand how would you make a link between two nodes? Could you explain that with
Yeah.
an example?
Yeah, so there's, if given some sort of edge list of graphs, you can always just, visualize them in our tool. But in the case of the word embedding, given some sort of glove word embedding, you have a high dimensional vector for each word. So what we did is just compute cosine similarity pairwise between every word, and just take some that are beneath, some small threshold. So just a way to generate a graph from a word embedding.
Right. Let's thank our speaker again.